So this problem basically gives you a few things to think about, kind of like how you're going to calculate delta H of this equation, the equation given in black out here, when you're given three different equations with known delta H values. This is actually an application of Hess's law of constant H summation. Right, Hess's law. And it's pretty simple actually if you know how to approach this kind of problem in the right way. Well, the first thing that you need to do is you need to look at these three equations given to you out here, and you need to figure out how you can put these equations together to basically result in this equation out here. And the way you do it is you can add, subtract, you can multiply them by a factor, or do anything you want. But you need to understand that whatever operation you perform on these equations, you have to perform similar operations on the delta H values. Okay, so let's see how you can solve this problem. There's one thing though you need to keep in mind, is that whenever you do this kind of problem, you don't need to worry about balancing equations. Most of the times these problems are given to you with the equations already balanced, so I wouldn't waste too much time trying to balance these equations because they're already balanced. Okay, so now that we have that out of the way, what I'm going to do is we're going to look at this problem very carefully, and we're going to see how we can compare these equations to that. So let's look at this 4NH3. Now out of these three equations given to you, which one has NH3? This one. But this has only half the amount of NH3. That means, that should tell you that you need to multiply this equation by 2 so that you get the same amount of ammonia out there, and consequently you'll have to multiply the value of delta H by 2 as well. So let's do that. So if you multiply that by 2, 2N2 plus 6H2 gives you 4NH3, and delta H multiplied by 2 should give you negative 183.6 kilojoule. Now if you look at this equation, you see 4NH3 is actually on the right side of the equation, and you need to take it to the left side of the equation, because in this equation given to you out here, it's on the left side. So basically you want to flip this equation around. So if you flip this around, this is what you should have. So all I'm doing is I'm taking the products and making them starting materials, and I'm taking the starting materials and making them into products. Okay, so once we have that, then delta H, when you switch an equation, that means when you flip it around, this delta H value changes its sign. Okay, so right now it's negative, so that will become positive. Okay, so now we have something set up which looks where the 4NH3 is in exactly the same position as that. Okay, now once we figured out the 4NH3, we want to look at the oxygens. Okay, because the oxygen is next on this. Okay, so if you look, there are 5 oxygens out there, and this equation has 1 oxygen and this has 1. So if you multiply this equation by a factor of 2, then you'll end up with 4 NOs out here, and that's exactly the number of NOs that you have out there. So let's multiply that by a factor of 2 and see what happens. I'm going to move this up slightly. Okay, I'm going to put that in a different color so that you don't get confused. So I'm multiplying this equation by a factor of 2. So you have 2 N2 plus 2 O2, which gives you 4 NO, and delta H has to be also multiplied by a factor of 2, and so that should give you 361.2 kilojoules. Okay, so once we've done that, we got to look at what else we have to figure out. So if you look at the equation out here, you figured out 4NH3, 5O2, So now if you look at this equation out here, you'll see that the only thing that you haven't accounted for is water, and you need 6 molecules of water. That means if we multiply this with 3, this equation by 3, then you have 6 molecules of water, you have 3 molecules of oxygen, and you have 6 molecules of hydrogen. Okay, so let's do that and see what we get. So I'm going to put that there. Okay, so we got to multiply that by 3, draw an arrow. Okay, you have 6 molecules of hydrogen plus 3 oxygen, 6 water, and delta H for this has to also be multiplied by 3, which would give you negative 1451.1 kilojoules. So now we have these equations set up. Now all you need to do is add these equations as they are. When you add these equations as they are, let me choose a different color. Notice very carefully. So we're going to add this one, and this one, okay? The nitrogen and nitrogen cancel out because they're on opposite sides, okay? Let's have a look. Hydrogen and hydrogen cancel out, okay? So what we're left with is 4 NH3 plus 5 O2 gives you 4 NO plus 6 H2O. Hold on, wait a minute. Is that the same one? 4 NH3 plus 5 O2, 4 NO plus 6 H2O? Yep, it is. So that's pretty cool, right? So anyway, so you see, once you figure out a few of them, the rest all fall into place. Okay, so the main trick is actually figuring out a few of them. I like to say that you have to have the eye of the tiger for this. But anyways, that's kind of funny. So if you add the delta H values of all of these, you'll actually end up with a value which is 906.3, negative 906.3, and that's really what you want to find out. And this is actually a pretty good application of Hess's law of constant heat summation.